next thing that I'd like to talk about is calculation of volumes by a method called the Disk and Wurtscher method. We're going to imagine that we have some solid shape that has circular cross sections, and that I'm going to take this shape and carve it up into very thin slices. You should think of pepperoni slices, for instance. These slices will each have a radius, a circular radius, and also a thickness or height that's perpendicular to the circular cross section. For now, I'm just going to call the radius by the word radius and the perpendicular height by perpendicular height. I want to think about how many cubic inches or cubic meters or whichever units you're using. How much volume does something like that have? Since it's a piece of a cylinder, we know that this is going to be the area of the face times the perpendicular height. But we also know that the area of a circle is pi times the square of the radius, so this is going to give us the formula that we're going to use. I want to think about the graph of some function y equal f of x, starting at x equal a and ending at x equal b. This time, though, it's not area that I'm interested in. We're going to reach into the picture, grab the x-axis, and use it as a handle to revolve this graph about the x-axis. By doing so, we generate a three-dimensional solid shape with a circular cross-section, and I want to calculate the volume of that region in three-dimensional space. As we usually do, we're going to chop one of the variables up into easier to deal with pieces. We'll look at the x interval from a to b, divide that up into a bunch of subintervals. If I think about the volume that comes only from the shaded in bit, then this is going to correspond to a small piece of the solid. Each one of the shaded in points is going to go around in a circle about the x-axis, and therefore will generate a disk. The plan is to calculate the volume of each such disk, add them up, and then take the limit as the norm of the partition in the x variable tends to 0. This will turn the problem into an integral. Then we do the integral using tricks from Calc 1. The only thing I have to worry about is to identify the radius and the perpendicular height. Since I've divided the x range up into smaller pieces, I'll have lengths delta x1, delta x2, and so on. Generically, I'll just think of one of them as being delta x number j. The shaded in strip will generate the indicated disk. As usual, we'll take a representative x value within chunk number j. I'll call it x equals c number j. We will pretend that the function f doesn't change much from the value f of cj on subinterval number j. We will use this as our representative function value. In this case, this is also the representative y-coordinate for chunk number j. When I revolve that shaded in strip about the x-axis, the furthest away from the axis of rotation that I can get is f of cj. This is going to be the radius of that disk. As previously mentioned, the volume of that one disk is going to be pi times radius squared times perpendicular height, which we now have ideas about. For one particular disk, the volume is approximately pi times the square of f of ci times delta xj, and once again I've written I where I meant to write j, so let me repair that. To get an approximation to the total volume, I'll add up the volumes of all of those disks, and then to make the approximation perfect, we'll do the usual thing. By now, this should be no shock to us that this is the definition of an integral, so we'll just write it that way. If you compare this against the thing that we found for the area under the curve, you'll see that there is a difference. If I was just calculating the area under the curve, presuming that the f is positive for convenience, this would just be the definite integral from a to b of f of x dx. But when we do the volume, it's different. The volume calculation is going to have a factor of pi, and not only that, you're not going to have a factor of f of x, you'll have f of x quantity squared instead. I want to look at the graph of y equals x squared, so f of x is x squared here. I want to revolve that about the x-axis starting at x equal 1, ending at x equal 2. I want to calculate the volume of the resulting shape. I want to think about this as literally as I can in terms of the things that we're talking about. The individual vertical strips, the width of strip number j, as usual, will be called delta xj. I'll have within that strip some characteristic x value, cj. Since I'm on the graph of y equals x squared, if x is cj, then the y-coordinate is going to be cj squared. Since my vertical strip goes all the way from y equals 0, which is the x-axis, all the way up to y equals c squared, then the radius of my disk is going to be cj squared. Our recipe says pi times radius squared times perpendicular height of the disk. So I'm going to have pi times the square of cj squared multiplied by delta x number j, and then it's business as usual. Add up the contributions from each one of the disks, take the limit as the norm of the partition tends to 0. This limit of a sum should be the volume of my three-dimensional solid. Of course, this is the definition of an integral. As usual, limit of sum transforms into an integral sign. The delta xj's turn into dx, and in all that remains, every place where I see cj, write down x instead. Actually, evaluating the integral is a routine problem, so details appear here. When the dust settles, we find out that the volume of our shape is 31 pi over 5 cubic units of distance. As a minor variation on a theme, I want to think about the region that is above the graph of y equal x squared, but below the horizontal line where y is 4. I'm going to revolve this around the horizontal line where y is equal to 4, so I'll generate this kind of solid shape. In this case, we're going to have to be a little bit more careful about how we calculate the radius. I am revolving around not the x-axis, but a line that's parallel to the x-axis. So it makes sense to split the x up into smaller pieces again, corresponding to the previous situation, except this time the axis is this horizontal line where y is 4, so this vertical strip is going to get revolved not about the x-axis, but about that line. The radius of the corresponding disk is, look at all of the points that go with this strip. How far away can you get from the axis of rotation? If you look at points that correspond to this one strip, the y can be anything from 4 down to c number j squared, but I don't want to include any of these points. I'm going to use the y-axis like a ruler. What is the vertical distance from 4 to cj squared? In the current situation, 4 is the bigger of the two numbers. The distance from the axis of rotation to the end of the strip is the radius. The perpendicular height is delta x number j as before. I'm going to write down pi times radius squared times perpendicular height, just as we've done before. Then, as usual, we'll add up all the contributions and take the limit. Limit of sum becomes integral. Delta x number j becomes dx. Everything else, stop writing cj, write the name of the independent variable instead, and we stated at the beginning that we were looking at x's that went from 0 to 2, so those are our limits of integration. The antiderivative is easy to get. When you evaluate it at 0, you just get 0, so basically I'm going to ignore that part. Only the part that goes with the x equal 2 contributes anything. After some arithmetic, that reduces down to 256 pi over 15. One of the things that we want to try to get away from is the belief that the letter x must always represent the independent variable. So let's look at this situation. I'm going to have a graph, but it's not y in terms of x, it's x in terms of y. I'm going to let the y variable range from 0 to pi. I want to revolve this about not the x-axis, but the y-axis instead, and figure out the volume of the resulting shape. Thinking of a typical strip in terms of the delta y's now, this will be a horizontal strip. When I revolve this around the y-axis, it's going to make a disk, the perpendicular height of which is delta y number j, the radius of which is going to be as far from the axis of rotation as I can get. That will be this x-coordinate. Within strip number j, pick a characteristic y number, which I'm still going to call cj. The biggest x-coordinate that I can get, as far away from the y-axis as I can get, is when x is the sign of whatever the y value is. If y is chosen to be c number I, then the right-hand end of this horizontal strip is going to be at x equals sine of c number j. I keep saying I instead of j. This is just out of force of habit. I want to figure out the volume of this disk. It's pi times radius squared times perpendicular height. Once we've done that, As usual, add them up and take the limit. The norm of the partition is the biggest of the delta y numbers now, not delta x. Except for the symbols being used, though, it's exactly the same idea. In this problem, the x-coordinates of the region that we're revolving go between 0 and 1, but the variable of integration is y, not x. For the points in the region, the y-coordinates can go from y equals 0, here at the bottom, to y equal pi up at the top. Officially, we don't know how to do this integral yet, but thanks to our side trip into trigonometry, we actually do. Sine squared of something is 1/2 times 1 minus cosine of 2 times something. I'll take the factor of 1/2 out. And antiderivative for what remains is easy to get. Antiderivative of a constant is the variable in question, which is y in this case. If y is the variable, 1/2 sine of 2y is an antiderivative of cosine 2y. The second term, 0 minus 1/2 sine of 2 times 0, is 0, so I'll disregard that. Sine of 2 pi is also 0, so all that remains is pi over 2 multiplied by pi. This is the volume of the indicated shape. So far, everything has been very concrete. I want to get an abstract fact now as well. I want to think about having a right circular cone with radius capital R at the base and perpendicular height capital H. It's important to understand that both capital R and capital H are constants. The radius of the cross-section of the cone gets smaller as I go from the base up to the top, but the capital R itself is a constant. It's the radius down at the bottom. I'm going to think about generating this cone by looking at the straight line in the xy plane that has y-intercept h and x-intercept r, and revolving that about the y-axis. Since that line has to decrease its height, its y-coordinate, by an amount h, in the change in x direction by amount capital R, it's obvious that the slope is negative, and in fact is negative h over r. Since I already know what the y-intercept is, the constant h, I can write down y equals negative h over rx plus h as the equation of that straight line. Since I'm revolving around the y-axis, I'm going to chop the y range up. The radius of the disk is going to be the x-coordinate on that downward sloping line. So this means I'm going to have to solve my equation for the line for x in terms of y, since all quantities have to be expressed in terms of y here. A little bit of algebra will show you that x is negative r over h multiplied by the quantity y minus h, then pi times radius squared times perpendicular height again. Add up the contributions, take the limit, the CJ's turn into Y's, the delta YJ's turn into dy, and if you look at the picture, the Y variable can be as small as 0 or as big as h in this particular situation. When you do the squaring, the minus sign in front of the r over h goes away. Pulling all constant factors out in front of the integral, I need to find an antiderivative with respect to y of y minus h squared. If you want to be picky about it, do a u substitution with u equal y minus h. In the end, though, you'll find out that the following is true. You'll find out that an antiderivative of y minus h squared is 1/3 y minus h cubed. Then we have to put y equal h and y equal 0 into that and subtract. H minus h is 0, so I'll disregard that. 0 minus h is the negative of h. I'm going to have 3 factors of that, which would give me 3 negative signs, 2 of which cancel out, the other one of which doesn't. 0 minus the negative of h cubed is h cubed. We have 2 factors of h downstairs, 3 factors upstairs, so 2 of them cancel out, leaving 1 remaining upstairs, and then just writing the factors down, we find out that the volume of a right circular cone with radius at base, capital R, perpendicular height, capital H, is 1/3 pi r squared h, which, if you look in a geometry book, you'll find out is the correct answer. So this is right. Everything we've done so far with the disk method has been based on disks. The volume of a disk is pi times radius squared times perpendicular height. We're going to make a minor variation on a theme. What if somebody removed part of this disk? They're going to remove part of the disk in a way that has the same symmetry, the same axis of symmetry as the original disk did. We still have the same perpendicular height, that hasn't changed, but we have removed some of the volume. How much depends on the radius of this hole that we've drilled down the middle of it. I'll think of the radius of the original as being the big radius, and the radius of the piece that we've drilled out will be the small radius. The volume occupied by this three-dimensional shape is the volume that we had originally minus the volume that we took away. So this will just be pi times the square of the big radius multiplied by the perpendicular height minus pi times the square of the small radius times the perpendicular height. Obviously, there's a factor of pi in both of those things, and there's a factor of the perpendicular height, so we can write this a little bit more briefly as this form. It's pi times the difference of the square of the big radius and the small radius multiplied by the perpendicular height. In the case where a central piece like this has been removed, this will be our recipe. This is called the Warscher method. I want to think about taking the region in the first quadrant that lies below the graph of y equal 1 minus x and revolving it around a straight line. But this time it's not going to be y equal 0, which would be the x-axis, or x equals 0, which would be the y-axis. I want to revolve this about the vertical line where x is always equal to 2. This graph has some interesting pieces to it. Most notably, if I tell you a y-coordinate, the furthest away from the axis of rotation that I can get within my region is always going to be on the y-axis. It's always going to be x equals 0. But the closest that I can get to the axis of rotation is not so simple. Down at the bottom, this distance is 1. Up at the top, this distance is 2, and in between, it will vary. So I'm going to have to be very careful about my chopping up and my distances and how I express things. Given a y number in subinterval number j, which I'll call c number j again, the small radius is as close as I can get to the axis of rotation within the strip I'm looking at. That would be that distance. I'll use the x-axis like a ruler. The small radius is 2 minus the x-coordinate on this downward sloping straight line. The big radius is 2. Because y is going to end up being the variable of integration, I have to express this x-coordinate on the downward sloping line in terms of y numbers. In particular, the y number that I'm going to pick out of subinterval number j. Since y is 1 minus x is 1 minus y, and if y is c number j, that would be 1 minus c number j. The small radius is the horizontal distance between 2 and 1 minus cj. And the large radius is always 2, so that's already been settled. So I have to take pi and multiply it by big radius squared minus small radius squared, then multiply that by delta y number j, add them all up, and take the limit. We'll wait till we finish the idea work to simplify the algebra. Business as usual. Limit of sum is integral sign. I forgot to write my pi down, so I put that back in. What's left on the inside is big radius squared minus small radius squared. Variable of integration is y, so the cj turns into a y, and all that remains is to put in the limits of integration. In this problem, y could be as small as 0 or as large as 1. This is now a routine problem. The antiderivative is 0 when y is 0, so only the y equal 1 contributes anything. When the dust settles, the volume works out to be 5/3 multiplied by pi, or 5 pi over 3, as most people would write it. You can make these kind of situations as complicated as you care to, but I think this is enough to get the main idea across. Next up is the shell method. I hope everyone's having a good day. I'll talk to you again soon.